All right, get ready to dive deep because today we're exploring the world of material science.
Oh, yeah.
Specifically, how AI is starting to shake things up
It is pretty wild.
big time. And we've got this super interesting research paper straight from Nature all about an AI model called MatterGen.
MatterGen, yeah.
And this thing is
It's really changing the game.
really changing the game.
It's tackling this challenge that's been a pain for material scientists forever, designing new materials.
Right, because I imagine that's...
It's always been the slow trial and error process, like
Yeah.
finding a needle in a haystack, but on an atomic level, so...
It's a good analogy.
Yeah, and expensive, right.
Oh, yeah.
Really expensive.
So how is MatterGen changing things?
Well, instead of just tweaking existing materials, MatterGen actually generates brand new stable materials from scratch.
Wow.
And it uses a method borrowed from image processing.
Got
You
it.
know, those AI tools that can remove noise from a blurry photo?
Right.
It's similar, but instead of pixels, we're talking atoms.
So this AI is like a digital artist, but instead of paintbrushes and canvases,
Yeah.
it's using atoms as its medium.
It is. And what makes MatterGen even more impressive is that it's not just throwing atoms together randomly.
Right.
It has to consider all these factors, the types of atoms, their exact position, and how they're arranged in this repeating pattern,
Okay.
called a crystal lattice.
Oh, wow.
It's like solving a ridiculously complex 3D jigsaw puzzle, but instead of finding the missing pieces, it's creating them.
Oh my gosh, how does it even know which atomic arrangements are going to work? Because I can imagine a lot of those combinations would just fall apart
Right.
in the real world.
That's where the power of machine learning comes in.
Okay.
So they trained MatterGen on this massive database of over 600,000 stable materials called AlexMP20.
Okay.
It's like giving the AI a crash course in Material Science 101, teaching it the fundamental rules of what makes a material stable.
So it's learning from the best, absorbing all this knowledge about what's already out there, and then using that to create something totally new.
Yeah,
That's pretty cool.
it is. And here's the kicker.
Okay.
MatterGen doesn't just create new materials, it designs them with specific properties in mind.
Oh, all right.
You want a material that's magnetic conductive or super strong, MatterGen can do it.
Hold on. Are you saying we can basically tell this AI what we want,
Yeah.
and it will whip up a material with those exact characteristics?
Pretty much.
That sounds like too good to be true.
I know, right? It sounds like sci-fi, but the research shows that it's remarkably good at this.
Wow.
And one of the keys to its success is something called an adapter module.
Okay, I'm intrigued.
Yeah.
What's so special about this adapter module?
Think of it like a set of fine-tuning knobs that researchers can use to tweak MatterGen's designs.
Okay.
It's like the super-powered design tool that you can customize
Okay.
to fit your exact needs. Want a material that's highly magnetic? Adjust the magnetism knob. Need something with a specific band gap for solar panels?
Mm-hmm.
Just dial it in.
So it's like having a materials genie
Kind of, yeah.
that grants your wishes. I wish for a material that's strong, lightweight, and conducts electricity. Poof.
MatterGen delivers.
Exactly.
Yeah, that's a good analogy.
Yeah.
And the paper gives some pretty mind-blowing examples of what MatterGen can do. But before we get into the specifics, let's delve a little deeper into what makes MatterGen so much better than previous attempts at AI-driven material design.
Okay.
Like, what's the secret sauce?
Yeah. Spill the beans.
Well, one key difference is that MatterGen focuses on creating materials that are not only new and unique, but also stable.
Right.
The researchers called this SUN materials.
Okay.
Stable, unique, and novel.
SUM materials. I love it.
Catchy.
Catchy and informative.
Yeah.
But why is this focus on stability so important?
Well, in the real world, you can't just throw atoms together in any random configuration and expect them to hold.
Yeah.
Most of those combinations would be too unstable
Right.
to exist for more than a fleeting moment.
So it's like building a house of cards.
Yeah.
You need a solid foundation. Yeah.
Exactly. And MatterGen's ability to generate these SUN materials is a huge leap forward.
Yeah.
In fact, the paper shows that it generates structures that are over 10 times closer to their ideal energy-minimized form.
Wow, 10 times.
Yeah.
That's a pretty big improvement.
It's a big deal.
Yeah.
It's starting to become clear why this is causing such a stir in the scientific community.
Right.
But let's get down to the nitty-gritty.
Okay.
How does this whole process actually work?
Yeah, I'm still a bit fuzzy on this whole diffusion process you mentioned.
Okay, yeah. So remember we said it's kind of like removing noise from a blurry image.
Right. Right, but instead of pixels,
instead of pixels.
we're dealing with atoms.
Exactly. So imagine you start with a bunch of atoms just scattered about randomly.
Hmm.
It's like having a box full of Lego bricks all jumbled up. MatterGen's job is to take that chaotic mess and gradually bring order to it, step by step.
So it's like tidying up a playroom, but on an atomic scale.
Uh-huh, yeah. But it's not just about arranging the atoms neatly.
Right.
It's about doing it in a way that results in this stable, low-energy configuration.
Okay.
Remember, nature always wants to be in the lowest energy state possible.
Right.
That's why water flows downhill.
Makes sense.
And that's why stable materials have their atoms arranged in a way that minimizes their overall energy.
So I'm following so far. We have this random collection of atoms, and MatterGen knows what a stable configuration looks like.
Yeah.
But how does it actually go from point A to point B? How does it like sort through all those possible arrangements and figure out which ones are going to work?
Well, that's where the diffusion process comes in.
Okay.
It's this step-by-step process where MatterGen makes tiny adjustments to the arrangement of atoms, always checking to see if those changes lower the overall energy of the system.
So it's like a game of atomic Tetris, where each move is guided by this principle of minimizing energy.
Haha, that's a great way to think about it. And what's really cool is that MatterGen isn't limited to just moving atoms around.
Okay.
It can also change the type of atom at a particular location.
Oh, wow.
So it might swap a carbon atom for a silicon atom, for example, if it determines that would lead to a more stable structure.
So it has this amazing ability to play with both the arrangement and the types of atoms.
Exactly. It has a lot of flexibility in its search for the perfect combination.
Wow.
And it keeps making these tiny adjustments guided by its knowledge of stable material structures until it arrives at a final design that is both novel and stable.
That's really it's like watching evolution happen
Yeah.
at warp speed.
Warp speed.
But instead of natural selection,
Yeah.
it's this incredible AI algorithm.
Yeah.
This is absolutely fascinating. It's like we're witnessing the birth of a new era
It is. It's pretty cool.
in material science, where AI is becoming like a real partner in the discovery process.
Definitely.
But tell me, why is this such a big deal?
Yeah.
I mean, we already have lots of materials, right?
We do.
Why do we need AI to invent new ones?
Well, it's all about pushing the boundaries of what's possible.
Okay.
The materials we have today have gotten us pretty far, but they have limitations.
Right.
Think about the challenges we face. Climate change, energy scarcity, the need for new medical treatments.
Right, yeah.
Solving these problems is going to require materials with properties that we haven't even dreamed of yet.
So MatterGen is like a tool that can unlock a whole new world of possibilities.
Exactly. And one area where this is really exciting is in the design of complex materials with 4 or 5 different elements.
Wow.
As you add more elements to the mix, the number of possible combinations just explodes,
Yeah.
making it much harder to find stable structures by chance or using traditional methods.
Right. I can only imagine.
It's like trying to cook a gourmet meal with 100 different ingredients. The odds of getting it right without a recipe are pretty slim.
Right. Exactly.
And MatterGen seems to excel in this complex realm.
Okay.
The research shows that for these more intricate materials, it actually outperformed traditional methods
Wow.
in terms of finding those elusive SUN materials, stable, unique, and novel.
So we're not just talking about like a faster way to design materials.
Right.
We're talking about accessing a whole new realm of possibilities
Exactly.
that were previously just completely out of reach.
Yeah, and there's another huge advantage.
Okay.
You'll appreciate this.
Okay.
Typically, once a scientist comes up with a potential new structure, they have to run these very complex calculations
Okay.
to verify its stability.
Right.
These are called DFT calculations.
DFT calculations.
Yeah.
Sounds intimidating.
They can be. They require a lot of computing power and time.
Oh, gosh.
But here's the cool part.
Okay.
Because MatterGen is so good at proposing stable structures right from the get-go, it significantly reduces the need for those expensive calculations.
Oh, wow. So it's not just faster in terms of the design itself. It's also more efficient in terms of the resources needed to, like,
Yes.
validate those designs.
Yeah, exactly. It's a win-win.
That's great.
And that cost saving could be a game changer
Right.
for accelerating R&D in all sorts of fields.
That makes sense.
But, all this talk about stability and efficiency is great, but I'm eager to hear about some real-world examples.
Yeah. Let's get to the juicy stuff. What are some of the cool things that MatterGen has actually been able to achieve?
Well, that's a story for the next part of our deep dive.
Oh, you're killing me. All right, folks, hold tight, because when we come back, we'll be diving into the specifics of what MatterGen can do, and trust me, you won't want to miss it.
It's a wild ride.
Yeah.
Welcome back. Before the break, we were just about to dive into some of the amazing things MatterGen has already accomplished.
Okay, yeah.
Remember we were talking about its ability to tailor designs for specific properties?
Right.
Well, the researchers put that to the test. Okay.
And the results are pretty mind-blowing.
Okay. Lay on me. What kind of material genie wishes has MatterGen been granting?
All right, well, let's start with something we all use every day, magnets.
Okay.
The researchers challenged MatterGen to design materials with this super high magnetic density.
Okay.
You know, the kind you need for powerful magnets that can do everything from, like, powering electric motors to storing data on your hard drive.
Right.
Yeah,
Okay, that sounds like a pretty tall order.
it is.
So how did MatterGen do?
It knocked it out of the park.
Really?
They trained MatterGen on this data set of, like, over 600,000 materials
Wow.
with known magnetic properties, and then basically set it loose with a specific goal.
Okay.
Create a material with a magnetic density of 0.2 angstroms to the power of -3.
Angstroms to the power of -3. That sounds pretty technical. Can you translate that into something maybe a little easier to grasp?
Sure, basically, it's a measure of how much magnetic punch you can pack into a given volume of material.
Okay.
So the higher the number...
The stronger the magnetic force.
Got it. So did MatterGen manage to hit that target?
It did.
Nice.
And not just once.
Okay.
It consistently generated a bunch of new materials with magnetic densities clustered right around that target value.
Wow.
It wasn't just a lucky shot, it was like a demonstration of precision and control.
That's impressive. Yeah,
Yeah.
it really does seem like this AI is capable of, like,
It is.
designing materials with pinpoint accuracy.
Yeah, and the potential applications are huge.
Oh, yeah.
Think about like electric vehicles.
No?
More powerful magnets mean more efficient motors,
Right.
which translates to longer range,
Uh-huh.
faster acceleration.
Right.
For data storage, imagine hard drives that are smaller, faster, and can hold even more information.
Yeah.
It's all about squeezing more performance into a smaller package.
Okay, I'm starting to see the bigger picture here.
Yeah.
This isn't just about creating cool new materials. This is about unlocking a whole new level of, like, technological advancement.
Exactly.
Yeah.
And that's just one example. Remember how we talked about band gap?
Yeah.
It's this crucial property for things like solar panels and semiconductors,
Right.
determining how efficiently they can convert light into electricity or control the flow of electrons.
Yeah, it's basically a measure of how well a material can harness the power of the sun
Yeah.
or the magic of electronics.
Exactly. So the researchers decided to test MatterGen's ability to design materials with specific band gaps.
Okay.
They trained it on a data set of about 42,000 materials
Okay.
and then set a target of 3 electron volts.
3 electron volts. Why that specific number?
Well, it turns out that a band gap of 3 electron volts is particularly useful for things like solar cells and high-performance electronics.
Okay.
It falls right in the sweet spot for efficient energy conversion.
So they were basically trying to design materials that could make our solar panels more efficient and our gadgets even more powerful.
That was the goal.
Okay.
And once again, MatterGen delivered. It churned out a bunch of stable, unique structures with band gaps right around that 3 electron volt target.
Okay, I'm starting to feel like a broken record here. But this is amazing. This AI seems capable of tackling any property we throw at it.
It really does, yeah.
What else did they test it on?
Well, how about hardness?
Okay.
They challenged MatterGen to design materials with incredibly high bulk modulus,
Okay.
which basically means resistance to being compressed or scratched.
Okay, so we're talking about super tough materials, the kind you'd want for, like, protective coatings
Yeah.
or tools that can withstand extreme conditions.
Exactly. They set a target of 400 gigapascals,
Wow.
which is about 40 times harder than steel.
40 times harder than steel.
Yeah.
Wow, that's some seriously tough stuff.
It is. And here's the interesting thing.
Okay.
For this particular challenge, they didn't have a huge data set to train MatterGen on. They only had data for about 5,000 materials with known bulk modulus values.
Wait, so even with limited training data, MatterGen was still able to design materials
Yeah.
with this extreme level of hardness.
That's right.
Wow.
It took a bit more computational muscle, but MatterGen managed to generate a number of stable, unique structures that met the target.
That's really incredible.
It was a real testament to its ability to learn and adapt even with less information to work with.
Wow. Okay, this is all incredibly impressive.
It is.
But I have to ask the million-dollar question.
Okay.
Are these just theoretical designs, or can we actually create these materials in the real world?
That is a great question.
It's one thing for an AI to dream up this cool new structure,
Yeah.
but it's another thing entirely to actually make it.
You are absolutely right, and that's exactly the question the researchers wanted to answer.
Okay.
They wanted to take MatterGen's designs out of the digital world and into the lab.
Yeah.
So they picked one of the materials it had designed for high bulk modulus. Remember that one?
Oh.
The target of 400 gigapascals.
Yes. The one that's supposed to be 40 times harder than steel.
That's the one. Okay. They fed MatterGen a specific combination of elements: tantalum, chromium, and oxygen.
Huh?
MatterGen crunched the numbers and came up with a structure for this brand new material.
Okay.
One that, as far as we know, has never existed before.
Wow.
They called it TAC-206.
CAC-206, it even sounds futuristic.
It does.
So they had the blueprint.
Yeah.
What happened next?
They took that blueprint into the lab and actually tried to synthesize the material,
Okay.
bringing MatterGen's creation to life.
Right.
And they use X-ray diffraction to examine its structure, confirming whether the real-world material actually matched the AI's prediction.
Okay. This is the moment of truth. Drum roll, please. Did it work?
Well, it wasn't a perfect one-to-one match.
Okay.
The synthesized material turned out to be slightly different from what MatterGen had predicted.
Oh, okay.
The types of atoms were all there in the right proportions,
Okay.
but their arrangement was a bit more random than in the ideal design.
Oh, interesting.
It was like the atoms had decided to do a little freestyle dance.
So, not a perfect replica. But I mean, that's not entirely surprising, right?
Right.
Going from a theoretical design to a real-world material
Yeah, definitely.
is bound to involve some challenges.
Yeah.
But the big question is, how did this freestyling material actually perform?
Well, they measured its Young's modulus,
Okay.
which is a way to assess a material's stiffness and resistance to deformation.
Right.
It's related to bulk modulus, so they were able to use this measurement to estimate the synthesized material's hardness.
Okay, so what was the verdict? Did TAC-206 live up to the hype?
The estimated bulk modulus was up to 169 gigapascals.
169 gigapascals, that's still incredibly hard. It might not be the full 400 that MatterGen predicted, but it's definitely in the ballpark.
Exactly. It's important to remember this was just a first attempt.
Right.
The researchers think the discrepancy could be due to that slightly more random arrangement of atoms in the synthesized material.
So with further refinements to the synthesis process, they might be able to create a material that's even closer to MatterGen's design and potentially reach that full 400 gigapascals of hardness.
That's the hope. This experiment wasn't just about creating one specific material. It was a proof of concept.
Right.
It showed that MatterGen's designs can actually be brought to life in the lab.
Right.
And that these AI-designed materials can exhibit the remarkable properties they were designed for.
This is seriously groundbreaking. It feels like we're on the verge of a materials revolution where AI is going to play a central role in creating the materials of the future.
It is really exciting.
Yeah, but I'm curious.
Yeah.
So far, we've been talking about designing for single properties like magnetism band gap, hardness. Can MatterGen design materials that have multiple desired properties all at once?
That's a fantastic question. It's one thing to design a material that's super strong.
Right.
But what if you also need it to be lightweight, heat resistant,
Right.
and made of readily available elements?
Right. It's like going to a restaurant and ordering a dish that's both delicious and healthy.
Exactly.
You want it all.
Yeah, and that leads us to one of the most exciting aspects of this research.
Okay.
The potential to design for multiple objectives simultaneously.
Oh, okay. I'm all ears. Tell me more about this multi-objective design.
All right, so imagine you're trying to create a new type of magnet, one that's not only strong, but also made of elements that are abundant and easy to source.
Okay.
This is a huge challenge in the world of magnets because a lot of high-performance magnets rely on these rare earth elements.
Rare earth elements. What's the problem with those?
Well, as the name suggests, they can be difficult and expensive to obtain.
Right.
They're often concentrated in specific geographical locations, and their mining and processing can have significant environmental impacts.
Yeah.
So there's this big push to find alternative materials for magnets that perform just as well,
Yeah.
but don't come with all that baggage.
This is like trying to find a delicious and nutritious meal that's also ethically sourced and environmentally friendly.
Exactly. It's a lot to ask for.
Yeah.
But the researchers wanted to see if MatterGen could tackle this complex challenge.
Got
They
it.
gave it this two-part mission.
Okay.
Design a material that has high magnetic density, remember that's a measure of magnetic strength,
Mm-hmm.
and a low HHI score.
HHI score. What's that all about?
HHI stands for the Herfindahl-Hirschman Index.
Okay.
It's basically a way to measure how concentrated a market is.
Right.
Or in this case, how risky a supply chain is.
Okay.
A lower HHI score means the element is more widely available,
Got it.
less likely to be subject to price fluctuations or supply disruptions.
So a low HHI score means a more stable and sustainable supply chain.
Right.
I like the sound of that.
Yeah. So they gave MatterGen these two targets,
Ah.
high magnetic density and low HHI score.
Okay.
They essentially asked it to create a high-performance magnet using ingredients that are abundant and easy to source.
So it's like giving MatterGen a shopping list.
Yeah.
With specific requirements. I need a magnet this strong, but please only use these ingredients.
Exactly.
Did it work?
It did.
Wow.
MatterGen, once again, rose to the challenge. It generated a number of stable, unique materials that hit both targets.
Cool.
They had the magnetic properties needed for high-performance applications,
Uh-huh.
but they were made of elements that are common, affordable, and readily available.
That's a game changer.
It is.
Imagine being able to create these powerful magnets without relying on those problematic rare earth elements.
It could revolutionize everything,
Yeah.
from electric vehicles to wind turbines,
Yeah.
making those technologies more sustainable and accessible.
Absolutely. And this is just scratching the surface of what this multi-objective design can achieve.
Right.
The researchers think that MatterGen could be used to design materials with even more complex combinations of properties.
Oh, yeah.
Imagine creating a material that's not only strong,
Yeah.
but also lightweight, flexible, and self-healing.
Self-healing materials. Now, that sounds like straight out of science fiction.
I know, right?
It sounds crazy, but with MatterGen, it might not be as far-fetched as it seems,
Yeah.
and the implications are huge.
Oh, yeah.
Imagine airplanes that can repair their own wings,
Wow.
or phone screens that fix cracks on their own.
Okay, now my mind is officially blown.
It's pretty wild.
This AI is not just designing new materials, it's designing a whole new future.
It really is.
But before we get too carried away with all these amazing possibilities,
Yeah.
I wanted to take a step back and ask a more practical question.
Okay.
How do scientists actually use MatterGen?
That's a great question.
Is it like a software program
Yeah.
they install on their computers?
MatterGen itself is this complex deep learning model.
Okay.
But the researchers have made the code publicly available so other scientists can use it and build upon their work.
Oh, wow.
It's what we call open source.
Open source, so anyone with the right skills and a powerful enough computer can basically download MatterGen and start designing their own materials.
In theory, yes.
Right.
Of course, it takes some expertise to use it effectively.
Right.
You need a good understanding of material science, machine learning, and how to work with these types of computational models.
So it's not exactly something I might be downloading on my laptop anytime soon.
Probably not.
Okay.
But the fact that it's open source is a really big deal.
Yeah.
It means other researchers around the world can jump and experiment with MatterGen and contribute to its development.
That's fantastic. It's a great example of collaboration and open science
It is.
in action.
Yeah,
Yeah, it's like giving the world a powerful new tool.
it is.
And saying, let's see what amazing things we can create together.
Exactly. And that's the spirit of this research.
Yeah.
It's about pushing the boundaries of what's possible, not just for a select few, but for everyone.
I love that. But I do have one concern. With all this focus on designing materials with specific properties, is there a risk of missing out on the unexpected? Sometimes the most exciting discoveries happen by chance,
They do.
when you stumble upon something you weren't even looking for.
That's a really insightful point. It's like when you go foraging for mushrooms,
Yeah,
you might be looking for a specific type.
right.
But sometimes you stumble upon something rare and delicious that you never would have found if you had just stuck to your list.
Exactly. So how do you balance this desire for targeted design with the need to remain open to those serendipitous discoveries?
Well, it's a delicate balance.
Yeah.
The researchers actually think that MatterGen can help with this.
Okay.
Instead of seeing it as a tool that dictates the outcome, we can use it as a starting point,
Right.
a way to generate a diverse set of potential materials
Uh-huh.
and then explore those materials further, looking beyond just the properties they were designed for.
So it's like having a map that guides you to this new exciting region,
Yeah,
but then you're free to wander off the beaten path
exactly.
and see what treasures you can find.
That's a great way to put it. It's about embracing both the power of targeted design and the wonder of the unknown.
I love that. This whole conversation has been such an incredible journey into the future of material science.
It's really cool.
It's exciting, it's mind-boggling,
It is.
and it makes you realize how much potential there is for like creating a better future
Yeah,
through the power of materials.
absolutely. We're just at the beginning of this AI-driven materials revolution, and it's hard to even imagine what the future holds.
All right, folks, we've covered a lot of ground today.
We have.
From the intricacies of MatterGen's design process
Mm-hmm.
to the mind-blowing potential of multi-objective design.
Exactly.
We've seen how this AI is not just dreaming up cool new materials, it's actually creating them,
Yeah.
bringing them to life in the lab, and paving the way for a future where materials science can help us solve some of humanity's biggest challenges.
It really is amazing.
But before we get lost in all the possibilities,
Yeah.
let's take a quick pause to let all this amazing information sink in.
Yeah, take a breath.
When we come back, we'll wrap things up with a look at the bigger picture.
Okay.
What does this all mean for the future of our planet, our industries, and even ourselves?
Big questions.
Big questions.
Yeah.
Stay tuned. You won't want to miss it.
Mm.
All right, we're back. Ready to wrap up our deep dive into the world of MatterGen.
Yeah, it's been quite a journey.
We've talked about how this AI works, its incredible capabilities, and even seen that researchers have managed to synthesize a material it designed.
It's pretty amazing.
It feels like we're on the cusp of a materials revolution.
Definitely a paradigm shift.
Yeah.
And what's so exciting is that MatterGen is just a glimpse into the future of material science.
Right.
It's showing us what's possible when we combine, human ingenuity with
Yeah.
the power of AI.
Okay, so let's talk about that future.
Yeah.
We've touched on some of the potential applications, but I want to hear your big picture vision.
Okay.
How could MatterGen change the world as we know it?
Well, imagine a world where we can design materials from scratch
Yeah.
to tackle some of humanity's biggest challenges.
Okay.
Take energy, for example.
Okay.
What if we could create solar panels that are so efficient
Right.
they make fossil fuels obsolete? Or batteries that can store vastly more energy,
Yeah.
making electric vehicles and renewable energy sources even more viable.
Those are some seriously ambitious goals.
Yeah.
Are we talking about science fiction here, or is this something that MatterGen could realistically help us achieve?
I think it's within the realm of possibility.
Okay.
MatterGen has already shown it can design materials with tailored properties like band gap,
Right.
which is crucial for solar cells.
Yeah.
And as the model gets better
Right.
and we learn more about how to use it, who knows what we'll be able to accomplish.
So you're saying that instead of being limited by the materials we happen to find in nature,
Right.
we could actually design the perfect materials for the job.
Yeah.
Materials that are precisely tuned to, harness the power of the sun or store energy with incredible efficiency.
Exactly. It would be like having a materials toolbox.
Yeah.
Where we can pick and choose the properties we need
Right.
to build a cleaner, more sustainable future.
Okay, I'm getting goosebumps just thinking about the possibilities.
It's exciting stuff.
But what about other areas beyond energy? Where else could MatterGen make a big impact?
Well, medicine is another field that's ripe for disruption.
Okay.
Imagine being able to design biocompatible materials that can be used to create artificial organs or tissues
Right.
that seamlessly integrate with the human body,
Oh, wow.
or drug delivery systems that target specific cells with pinpoint accuracy,
Wow, that's amazing.
minimizing side effects and maximizing effectiveness.
We're talking about like extending lifespans, improving the quality of life,
Yeah,
and potentially even curing diseases that are currently considered incurable.
potentially, yeah. It's pretty amazing.
It sounds almost too good to be true.
I know, it's mind-blowing. And it's not just about treating diseases,
Right.
it's about enhancing human capabilities.
Yeah.
Imagine materials that can repair damaged nerves or enhance muscle strength.
Right.
The possibilities are truly limitless.
This is all incredibly exciting.
It is.
But as with any powerful technology,
Yeah.
we have to consider the potential downsides.
Of course.
What are some of the ethical considerations we need to keep in mind as AI-driven materials design becomes more widespread?
That's a really important point.
Yeah,
Any powerful tool can be used for good or for ill.
right.
We need to be thoughtful about how this technology is developed and deployed.
Yeah,
For example, we need to make sure that these new materials are safe for human health and the environment.
right.
And we need to be mindful of the potential for job displacement as AI takes on more tasks traditionally performed by humans.
So it's not just about the science, it's about the societal impact as well.
Exactly.
Yeah.
We need to make sure that this technology benefits humanity as a whole and doesn't exacerbate existing inequalities.
Right, right.
We need to have those conversations now
Yeah,
before this technology becomes so pervasive that it's difficult to control.
right.
It's about harnessing the power of AI for good
Yeah.
while mitigating the potential risks.
I completely agree. This feels like one of those moments in history
Yes.
where we're standing at a crossroads.
Yeah.
We have this incredible new technology with the potential to transform our world for the better, but it comes with responsibility.
It does.
Yeah,
It's up to us to use this technology wisely
Right.
to shape a future where AI and human ingenuity work together
yeah.
to create a more sustainable, equitable, and prosperous world.
Well said. So what does this all mean for you, our dear listener?
Yeah.
It means that you're living in an era of unprecedented scientific advancement,
It's pretty amazing.
an era where the very materials that make up our world are being reinvented.
It's true.
It's a time of both great opportunity and great responsibility.
Stay curious, stay informed, and don't be afraid to ask the tough questions.
Yeah.
The future is being written right now,
Yeah,
and we all have a role to play in shaping it.
absolutely. And on that note, we're signing off.
Thanks for listening.
Thanks for joining us on this deep dive into the world of MatterGen and the future of materials science.
Yeah, it was a lot of fun.
We'll be back soon with another fascinating exploration of the cutting edge of science and technology.
Definitely.
Until then, keep those minds curious
Yeah.
and those imaginations fired up